So previously we looked at reviewing some of the light stuff you guys did in grade 11. So we did a whole bunch of that stuff. We looked at reviewing what happens when light changes mediums. We looked at the Young experiment. We looked at Snell's law. We just a whole bunch of stuff that you guys did in grade 11, and we reviewed a bunch of that type of thing. So when we're looking at light, of course, is what we're sort of focusing on right now. And you guys have used Snell's law, you guys have done the Young experiment, all that type of stuff. You applied Huygens principle to the Young experiment. There's a whole bunch of things, the interference patterns, all that type of stuff. And these things like Snell's law, the Young experiment, and we can even incorporate things like Huygens principle. We looked at that, we incorporated that as well. All these different things that you guys looked at, and they, of course, all focused on the wave nature of light and showing sort of how light works. Now, one of the problems that they still had way back when, one of the problems, we've mentioned this before, is, of course, how does light go through a vacuum? Okay, so they didn't understand how light can go through a vacuum because, of course, waves need a medium to travel through. And there's a bunch of theories and a whole bunch of stuff out there. There's like ether theory. There's a whole bunch of theories that are out there that we're not going to look at how that worked, but they didn't understand like a vacuum, especially, like in a lab where you take a vacuum tube and you suck out any possible material that could possibly be inside, and light still goes through it. They still didn't understand how that was possible, how that could work. Okay, so what we're going to do is we're going to look at a little bit of a different situation here. And I'll try and, this actually, I think that one of my profs showed me in university, and that's how he taught us. So I'm going to do the same thing with you guys. We're going to start with a couple of wires. So that's what these are. These are going to be wires, and they're not going to be connected to each other. Something like this. Okay, so here we have two wires, and these two wires are going to have a charge in them. And we're going to say that this one's got positive charge and this one's got a negative charge. So you've got a positively charged wire and a negatively charged wire. When you get a positively charged wire, they of course will have an electric field between them. And I'm going to draw it like this, from positive to negative. There's my electric field, something like this. Okay? So nothing crazy, nothing weird. So like a parallel plate idea, except they're bent. Okay, all good? Now, what I'm going to do is I am going to, actually I'll just copy and paste this here. I'm going to copy, paste. Okay. Now, what if instead, get rid of that. What if instead I reduce the charge on the conductors? And I'm going to represent that by just drawing the charges something like this. So I've reduced the amount of charge. Well, if I reduce the amount of charge, my electric field is going to get weaker. So I'm going to draw something like this. So it's a weaker electric field. But what happened to the electric field that I started with? Well, fields don't just disappear. They radiate out into space to keep on going. So this electric field will have moved out. It'll have moved on, so to speak. So maybe it's out here. And then what I'm going to do is I am going to take the charge away. I'm going to make zero charge. And then what I'm going to do is I'm going to reverse the polarity. So I'm going to take these two and I'm going to flip them and make the field stronger. And then I'm going to make the field weaker again. I'm going to, cancel it out, flip the polarity again. I'm going to keep on cycling through. And if I would do that, if I kept drawing the electric fields, they would actually look something like this. Okay, so I kept on taking the polarities and I kept on reducing them and flip-flopping back and forth, I would get something that looks like this. And, just looking at it, you can probably sort of see what's happening here. We've actually created an electric field wave. We actually get an electric field wave by doing that, okay, which is kind of cool. So I'm going to show you a little animation here for which will actually show this really nicely, and then we'll keep on talking about this a little bit, okay? Okay, so I got my two charges, and I'm going to get them to go. So they're going to move. So they move up and down like that. So instead of me fluctuating the charges on this nice little animation here, it's got the charge going up and down. And as the charges go up and down, there's the electric fields that are being given off. And you can see that they actually create an electric field wave that moves out. Okay, so that's the basic idea what we're talking about. So you can actually create an electric field wave, which is kind of neat. All right. Now, you guys have worked with electric fields for a while now, and you've done different things. But one of the cool things about electric fields is these guys don't need a medium. I mean, you can put electric fields through a medium, but you don't need to put them through a medium. So you've actually created a type of wave that actually doesn't require a medium to actually exist. And so then this can help to answer the whole question of how light goes through a vacuum, because you actually now have a wave, no medium required, that can permeate through empty space, vacuums, whatever you want, which is really cool. Now, the thing is, though, this is where one of your other ideas kicks in that you guys were working on in your induction stuff. What we have here is charges moving up and down. All right, we've got charges going up and down. And if you've got moving charges going up and down, well, moving charges, these guys actually create magnetic fields, like current in a wire. That's basically what they are. Moving charges create magnetic fields. Not to mention, if you go back to your induction stuff, if you got a changing electric field, well, you guys use changing electric field to create or induce magnetism. And of course, inducing magnetism can induce currents and voltages and all that kind of stuff. And the two things sort of go back and forth. And the two things, the electric field that's changing, the magnetic field that's changing, these two things sort of create each other and they feed off each other. So we've got these two fields. We've got the electric field and we've got the magnetic field. And the way I like to think about it is sort of like they're sort of like feeding each other. So they're also like sort of creating each other. So this goes against with Huygens' principle that waves recreate themselves at all times. That's sort of what's going on here. The changing electric field creates the changing magnetic, and it keeps on going. And it's the term sometimes you'll hear is self-propagating. So it's sort of creating itself, propagating. We'll actually just write it. It's actually self-propagating. It's actually recreating itself like Huygens' principle. So this is a very much of a Huygens idea, where the waves can recreate themselves and self-propagate. So not only do we have an electric field going one way, we've also got a magnetic field. Now, if we draw the magnetic field for the wire, it would be going around something like this. If you notice, it's actually perpendicular to what the electric field would look like. So instead of just having electric field by itself, you also get a magnetic field. Okay, so I'm going to show you a little animation on that. So this probably looks familiar. You've probably seen something like this before, but here we have the electric field going sideways and magnetic field going up and down. We'll press play here, and we get something like this. And you can see that the two fields are moving, and they're moving perpendicular to each other. And it has to do with how they're created and how they actually work. And this is a wave made of electric fields and magnetic fields, and they're continually recreating and feeding off each other using the induction stuff that you guys have taken to keep on going forward. And this is the idea behind an electromagnetic wave. And you guys have heard of electromagnetic waves before. So this right here, this whole idea, this is what's called an electromagnetic wave. And of course, electromagnetic waves, these guys do not require a medium. So it makes sense that this could possibly be light. Okay, now this is the work and ideas coming from a guy named Maxwell, and he's like from the 1860s. And Maxwell, James Maxwell, super crazy genius with induction, electricity, and magnetism, all that kind of stuff. And he did some really cool work with electric and magnetic fields and induction. And so this idea sort of comes out of his stuff. So it's a good chance that this is how light could actually work. And of course, you guys know that you often talk about light being an electromagnetic wave and the electromagnetic spectrum and that type of stuff. And this is the basic idea behind how electromagnetic waves are actually made and that type of thing. Okay, so let's look a little bit more at what Maxwell came up with. So Maxwell did a ton of work with electromagnetism and that type of thing, and he came up with Maxwell's equations. And I'm just going to write them out. You guys aren't expected to know these. I mean, this is more advanced math than you guys take, but I'm going to show them to you anyway. The first one, this is a lot of the calculus notation, and there's four equations, four Maxwell's equations, and the first one No, let's do it the other way. Let's do it the other way. Oops. First one is okay, something like this. So I'll clean that up a little bit. And I don't expect you guys to understand what that actually all means, but you should recognize some of the stuff. Basically, this is an integration symbol, means to add up. And you're adding up the electric field over an area. It's directly connected to how much charge there is, which is Gauss's law type stuff. If you recognize epsilon naught, that is from the K value that you guys use with your electric field values, which is 4 pi epsilon naught. It's the same one. So this is one of his equations. It has to do with electric fields coming from charges. The second one has to do with magnetic fields. And basically, you know, you add the magnetic field over an area, the flux is always going to be equal to 0, which is something else you guys take. And whenever magnetic fields go out, they eventually come back in, that type of stuff. All right. The third one, change that to a C. And let's see. That. All right. Okay, again, you're going to recognize some of the symbols. You've got magnetic fields, you got lengths, you know, like lengths of wire and stuff like that. Okay, and the fourth one, this is the biggest one, something like this. BDO. Mu naught, you should recognize that from your magnetic field stuff. There's I for current. Again, I don't expect you guys to know this, but you guys have been using the results of these formulas in your entire fields unit for a while. All right, so those are the 4 Maxwell's equations. Basically, they lay down the groundwork for almost all the electromagnetic field stuff that you guys have been working on, all of your field stuff. So it's crazy what you can actually do with these things when you actually change their forms and apply the calculus and that type of stuff. Now, the important thing for these guys is not expecting you guys to actually use these in these forms, but what's really, really cool is when you actually study these formulas, they actually predict the actual wave nature of light and how they should actually work. And what's really, really cool is if you take the magnetic constant and the electric constant, the mu naught and the epsilon naught, if you take those two and you square root them and you take the inverse of them, you actually will get the speed of light. So it's really, really cool when you take these equations and you put them together. You take the magnetic constant, the electric field constant, the mu naught, the epsilon naught, you put them together, you can actually get the speed of light, and actually predicts the wave nature of light as well as electric fields and magnetic fields. So aside from predicting the wave nature, you're able to actually predict the speed of light, the C value, which is really, really neat. And it's really cool is there's no wavelength or frequency limitations. So there's no wavelength, there's no frequency limitations. So all forms of light actually have the same speed. There's no frequency or wavelength in this expression, it's just the mu naught epsilon naught, that's it. So no wavelength, no frequency limitations, all light has the same speed, and you know, they all have very, very similar properties as waves, so you can apply all the wave stuff to it. And these are the big things that came out of Maxwell's equations, not just explaining how electric and magnetic fields work and that type of stuff, but attaching this to light and predicting the speed of light and showing that all light should have the same speed, and all that type of stuff that came out of it is absolutely amazing. And this even applies to what you guys have done in chemistry and that type of stuff, where you guys have done, you know, there's the nucleus of an atom, and we've looked at electrons in orbits, and electrons go up and down between different orbital shells to produce light. We talked about that type of stuff. Well, there's no difference between these electrons going up and down and the charges going up and down. And when those charges go up and down in their orbits, they act the exact same way as the simulation I showed you. They produce fluctuating electric fields, which produces, you know, the moving charge. They produce fluctuating magnetic fields. And that's why it's all through this stuff when charges, electrons, change orbits, and they can actually produce their spectral colors and produce those different colors of light that you do in spectral analysis. So this is what came out of Maxwell's equations, and it's really, really important in that type of stuff for induction, electric fields, magnetic fields, and all that kind of stuff. And he showed how light works and how light can actually go through a vacuum.